So, hi everyone, welcome to our event. This event is brought to you by Datalogs Club, which is a community of people who love data. We have weekly events, and if you want to find out more about the events we have, there is a link in the description. Click on that link and see what we have in our pipeline. Actually, we are scheduling like a ton of new podcast interviews. Like I think we have 5 or 6. So you need to watch out. There will be announcements, and this page is where you can see them. Also, do not forget to subscribe to our YouTube channel. This way you will also get notifications about streams like the one we have today. And we have an amazing Slack community where you can hang out with other data enthusiasts. During today's talk presentation, you can ask any question you want. There is a Slido link. It's pinned in the live chat. Click on that link, ask your questions, and we will be covering these questions after the presentation. So I think that's all. I did not forget to say anything. Hagop, Andreas, now the floor is yours. Please share your screen and let's start.
Thanks, Alexei. Okay, so I have to remember how actually. I have to give permission to share the screen. Okay, this is guys.
You don't use Zoom at Zalanda, do you?
Oh, no, bro, just give me 2 seconds. I will.
Yeah.
Already leaking details. Oh my God.
You mean about the company where you work?
Yeah. Oh my God, we're not using Zoom? No. I imagine, okay, so if you were to estimate, how often does the permission sharing happen? Then we can estimate the Zoom adoption.
Not that. Like I don't remember last time it happened actually.
Oh my God.
Yeah.
Wants to adopt a late majority?
Yeah.
Everything is going well.
Not everyone is on Mac. That's also like on Windows or on Linux. You don't need to do that.
All right. Andreas, Alexei, are you seeing the screen?
Yep.
Yes.
Sorry. Oh, yeah. Perfect. Then sorry about for that, for the short, interruption, but at least now we can share and everything is fine. Okay. So hi everyone. So today we will be with Andreas talking about inventory optimization and e-commerce. And the good thing is that we're not only going to talk about it like in a theoretical way or from far away, but we're going to actually base it on our experience at Zalando and really share what we learned, what type of issues we met, and what type of solutions we ended up finding. So I remember I was talking with a couple of scientists and from different companies, like they do either food delivery or they are like pure e-commerce. And I remember like this topic of inventory optimization is a big one. And we will see that actually lately this topic even become a bigger one due to basically the topics of cost optimization and also being efficient in the way we do operations. So I'm hoping that this conversation will be interesting and that we will be having fun and hopefully we can also catch up after that. Yeah. So before we do that, I would like to maybe give us like a short introduction of ourselves. So hi everyone, I'm Hagop, senior applied scientist at Zalando. Have been working at Zalando for now 3 years almost and doing applied science for the last 6-7 years. I had the pleasure to also work with Alexei. And so I'm usually very passionate about anything that touches like data science, deep learning, like in specialty, green tea, cycling, and running on my personal time. And also my biggest hobby is my son, who probably can be joining in the room at the call. So I hope that's also fine. And on that, I would like to give the floor to Andreas for the presentation.
Hey everyone, Andreas. I'm a principal applied scientist at Zalando. I've been here for roughly 2.5 years. And somehow throughout my career, I always end up doing logistics. Never really planned it that way, but here I am. And I guess also I do things outside of work. Usually it involves some kind of board sport or tabletop role-playing games as a big activity for me. It's a great way to keep touch with old friends.
What is a board sport?
Snowboarding,
I see.
skateboarding. Yeah.
Got it.
You got 2 feet on a board. And you
2 feet on the board is a good description of this.
Yeah.
Okay. But Right. Okay. So yeah, so this was us. Contact us afterwards. We're pretty nice, I think, I hope. So yeah, don't hesitate. But before we do, super important, we are obviously the ones presenting the work and the learnings, but it's not only the two of us, right? So the effort has been done by a bigger, by a much bigger team. And actually, we'd really like to thank them before we even start, and that you also remind that if you need any information, you can also, have contact with with any member of the team. And yeah, so thanks to them. So super important.
I specifically call out, if you look in the bottom right, the little purple ribbon there.
Exactly. Hiring. That is also true. So the team is also hiring, like depends on the position. Sometimes data engineering, sometimes it's applied science, or probably also machine learning engineering, depending on the time of the year. Yeah, so please stay tuned, and also happy to meet you for that purpose. So very important. Good that you reminded us. Very nice. Okay, good. So the agenda for today, we will basically try to be doing it in 30 minutes, 40 minutes, and then we have time for the questions. And the plan is very simple. So we will start by saying, okay, so what's even like the problem of inventory optimization? There is a lot of, let's say, misunderstanding about the topic. Several people say inventory optimization, but they always mean different things. So we're hoping that this time, we really kind of set up that and try to anchor like the discussion. Based on that, we will basically talk about what are inventory policies and what type of equations we're even trying to optimize, right? Like what's the cost equation that we're trying to optimize? The limitations of deterministic optimization that are very, very common and often baselines in this type of exercises. And, just review overall optimization approach and use techniques that you found, but also we tried, and the one that we are actually betting on in production and hoping to develop in the future. And there will be like a very small particle, like a technical part that is very important. We will be basically talking about how we took all this theoretical concept, right, and we make it and we made it real, and how we ended up basically having something that for those who do inventory optimization, this number seems pretty familiar. We're basically able to optimize for a given SKU or a given article in less than like 200 milliseconds. Which, if you think optimization, you usually think of seconds of minutes. So we actually managed to reduce that to something that is renewable and also real time. And we're hoping that we also discuss some, let's say, technical implementation topics and see how we did this. It's also pretty interesting. So not only theoretical and mathematics, but also applied concept behind and some ML ops concepts. So that's the agenda. And at any time, ask questions. We're more than happy to stop or even take them at the end. Good. Then Andreas, you can, I guess, start with the mental condition topic.
Cool. And I'll rely on you for pressing the button.
Sounds good.
It is. So first of all, kind of 10,000 feet view. So let's take a step back and think about, okay, so we're in applied science, we're trying to solve a problem. How do we approach this inventory optimization problem? And there's this model that we like to think about. So essentially, almost all applied science problems have these three components. You got a decision, a policy, and some inputs into your policy. Now, what's the decision? I mean, this might seem obvious, but it's important to recognize, right? I used to call this the money moment. So when in real life does something happen where the world diverges into two parallel universes, one where you make more money and one where you make less money, for example, and kind of identifying this point. So I've given some examples here. So for example, you're working in insurance, there's a decision to approve an insurance claim, right? And if you're correct in that decision, there are some outcomes. If you're wrong in that decision, assuming there's such a thing as wrong, there's some other outcomes, and this is the goal, right? To optimize this decision. It could also be you decide to increase the rotor thrust on a drone, or that you decide to ship 100 items to the warehouse, right? And then working backwards, then you'd say, okay, so if I now want to optimize my decision, then I need to find some policy to take that decision. Still, right? Even in classification, you end up deciding on your thresholds, and the classification threshold, of course, impacts your the cost picture or the outcome picture of then using, let's say, a classification model. You also see a policy in control theory, right? So if you're having a drone, you might have an LQR controller running in there. and that acts as a policy. And in our case, for replenishment, you might look at an RSQ policy. Now, Hagop will tell you more about those in a second, but there'll be a policy, right? And to run any kind of policy, you of course need some inputs. And some of those inputs, they're known. Maybe you just query your database, you have them. And some of those inputs you don't have. Perhaps in the replenishment use case, you'd be wondering what is the upcoming demand. Obviously, the future isn't in my database, so I need to estimate that. For example, if you're running a drone, you do state estimation, right? And so the data that you don't know or that is uncertain, you do estimates. In the claims situation, you might use a classification model as input into your policy. So kind of this is the overarching model that we want to apply. And Hagop, if you click the space, I guess.
Yeah.
So here, and I already alluded to this, right? But so how does this look in our case? Well, in our case, you have some supply planner, and they're sitting at work, they're going through the inventory, and they're deciding to ship a given number of a given article on a given date to a warehouse, right? And this is where fundamentally the outcome is decided, right? And this is the decision we need to optimize. Then you look at the policy. So a replenishment decision, it consists of what, when, how much you decide, and what you want to do is you want to optimize for profit, right? Or you might have some other goal, but let's use profit now. It's a very convenient when you can get that far. And then for these, what are the inputs? Well, to do this, you need to know the current stock level. This you probably know in your database. And you need to know the upcoming demand to anticipate it. And this you probably need to estimate, right? And you might want to understand your resellable returns and so on. So this is now kind of having the overall mental model. Let's now zoom into how you might approach the inventory optimization problem. Inventory optimization in e-commerce. Let's go. As I already mentioned, right, what we're looking at is what, when, and where, right? So this is fundamentally what replenishment is about. You need your inventory to be there when the customer is ready to buy. Now you need to decide when to put it there. If you put it too early, you end up storing inventory for a long time. And if you put it there too late, you might have what's called a stock out, which is when you're out of inventory. And any customer coming to buy your product, they're now not able to purchase it. And then, of course, just like you need to be there at the right time, you need to be there at the right location. So if you can't ship to the customer when they're ready to buy, then, of course, you're not able to close the sale. So fundamentally, these are the sub-questions. Now let's dig a little bit deeper into this. So how might you understand this decision in terms of outcomes? So a simple kind of traditional model of how you look at this, you'd say you're getting some inventory from a supplier into a warehouse. You'll incur a cost shipping from the supplier to the warehouse, probably also unpacking into the warehouse and so on. In addition, of course, if you're buying it from a supplier, you need to pay the supplier for the goods. So now you bound up some capital, the inventory is sitting in your warehouse, and then the customer comes to buy it. And then you incur an outbound processing cost. So the customer makes a purchase, you got to ship it to them. Your shipment supply chain is then gonna, of course, incur a cost. Now, in reality, as is customary when you come to reality, it isn't that easy. So here we're developing a few more of the factors, right? So often, especially in online commerce, you have a significant amount of returns. After selling to a customer, you might actually have to pay for processing a return from that customer. But on the other hand, many items that are returned, you could potentially sell again, right? So kind of silver lining. Then in addition, you need to understand, well, what opportunity did you lose with your actions? So for example, if you didn't have inventory in your warehouse when a customer was there to buy, you had a lost sale, right? And so you could understand that as an opportunity cost. of being out of stock. And on the contrary, if you're having a bunch of inventory sitting in your warehouse doing nothing, not only is it accruing a storage cost, but also you might have done something else with it. Let's say you're having both physical stores and online e-commerce. You might then say, okay, if it was just sitting in the warehouse, I might have put that in some of my retail stores. So there's, of course, an opportunity cost of overstock too. So yeah, breaking this down, or rather developing on this, so there are some practical constraints too. So we, in the real world, usually have pretty complex systems. So in our situation, we're talking millions of different articles, right? A lot of decisions to replenish. We're also having what's, to use a fancy term, multi-echelon system, right? So you got multiple warehouses, multiple types of warehouses doing different types of operations, and flows between these warehouses. They might even cost different depending on which direction you're shipping things. Then you also have seasonal goods, right? So perhaps if you're selling black socks, you could sell those all year, every year. But for example, shorts, you probably only sell in the summer and sometime in the winter when people go to vacation. So the value of shorts sitting in a warehouse varies over time. And then, of course, what I already mentioned before, often you see pretty high return rates, so you can't assume that returns is a non-significant part. Actually, the way it rather turns out is much of the inventory you have on hand because of a return. Yeah. So to add to this, right, you have a lot of uncertainty in supply chains, and arguably the job of a supply chain optimizer or supply chain planner is really to deal with the uncertainty. If you knew exactly what would happen in the future, if you knew exactly how many items a customer would want to buy, you could easily do some plus and minus and figure out how much you need in the warehouse. But of course, that's not the reality. The weather changes customers' purchase patterns. You have fundamental uncertainty in demand. You know, someone about to click buy and they get distracted by their family, right? Fundamental uncertainties. You got economical factors that you can't really predict, as we know. We have pandemics, geopolitical tensions, trade barriers, all kinds of things kind of coming in and messing up your nice mental model, right? With all of this said, let's get a bit more concrete. So how might it look then? Like if we're really coming down to what would a mathematical model of this look like? So at a very high level, at least what we're proposing here, you want to maximize profit contribution. What do you do this? Well, you do this with respect to your revenue, storage, the lost sales opportunity cost, the overstock, the opportunity cost of having overstock, and the cost of the operations you need to go through to actually carry out your replenishments. And so here I put in a very simplified form a kind of optimization problem, and later on you'll see how we tackle that. In reality, of course, this becomes a constrained optimization problem, and there's a whole question about how you estimate the objective function and so on. Cool. So I believe I'm now handing over to Hagop.
Yeah, thanks, Andreas. So basically, now that we know the environment in which we operate and also the problem that we have to solve, right? So how do we do that? So that's why we're going to talk about inventory policies, right? And the cost equation to optimize, basically. So the first thing is the policy, right? So some who maybe have worked in reinforcement learning or supply chain or operation research might be more familiar with it. But what does a policy mean, right? So basically a policy is us trying to narrow down kind of like the dimension of the problem, right? So we're trying to narrow down the decision space, right? And the decision space is called like the inventory policy. So there are like a lot of them in the literature, and we can give some very simplified examples. So like the most common ones that are, let's say, more school examples is what we call the SQ policy or the RS policy, right? For example, the first one, which is the SQ policy, is when you basically define a point from which you trigger a replenishment or a production order. And Q is the quantity that you basically order or replenish. So let's say you reach a certain point S, right? Then at this point, you decide to trigger your replenishment or your production decision with certain lead time. The quantity that you ordered actually comes up a couple of days later. Then the inventory sorts out until it reaches again the same reorder point. With the lead time, you order a quantity, etc., etc., etc. And the other pattern would be, for example, where you design what we call like a review frequency and a max to order, right? Where basically every 2 weeks or every 3 weeks or every 1 week, depending on the R, you basically automatically trigger a replenishment or a production decision until a certain point, right? So then you basically, let's say every R, this can be any date, right? Any period. Every like a specific R, you basically automatically trigger, the decision is taken with some lead time, then your basically replenishment or your inbound happens, then your stock is updated, and etc., etc. The good thing about this is that really you're trying to make basically very complicated decisions and trying to reduce the space in a low dimensional space where it's actually even feasible to solve like the problem, right? So let's say for every SKU, so every article, we want to find like these optimal values and which ones they be. The first question is, wait, so which one do I choose, right? So you said that there are many and you just gave us 2 examples. Actually, there are a lot. And not all of them are realistic. Some of them are simplistic. They do not work. But so what we can say about them is that most policies actually do have some nice properties in theory, right? So they're very good school examples where you can study and like learn the concept. But most of the time, we actually fail to satisfy some of the assumptions that they're based on. For example, they are not adapted for articles that are extremely understocked at the start, right? So if you're having a seasonal good, let's say at the start of your sales season, you have almost no inventory, or even after the stock out, you have no inventory. So basically, you don't know how to handle that case. Most of the time, they make the assumption that we have like some sort of constant demand, right, with unlimited window of sale. So the concept of season or the concept of perishable good, basically with an end of like lifetime for that article, doesn't exist. They assume that you can basically be selling or replenishing this article forever, which is not great, right? And what really also bothers is that they make the assumption that most of the time your demand is stationary, right? That it follows like a constant demand, and it's like, let's say, like some sort of Poisson process, but it doesn't have high season, low season. Like it doesn't have this a constantly evolving trend, which is not really realistic. So we really took this, we're like, okay, so how can we end up having a policy, right, that still kind of simplifies our life and makes that the decision space is small, but actually is adaptable to a real use case. So we ended up taking what we call the RSQ policy, and we adapted it a bit. So the RSQ is basically every week or every period R, every review period R, I check if I am reaching the limit. And if I do reach that limit, I basically, order a certain quantity to replenish or either to basically produce an inventory automatically. That is simplified, and we were like, okay, so this still doesn't work. We have to adapt it further. So we basically took this and then we added some parameters in it. So we kept R, S, and Q, but we added 3 terms that are very important. We added the first next replenishment week index, right? So if I'm today and I'm making this optimization now, or if I'm making it tomorrow, what would be the next recommended, or what would be like the next optimal time at which I should basically trigger my next replenishment? And what should be the quantity Q0 for that replenishment? Why do we basically have a major focus on the next replenishment is that, well, obviously the concept of, SQ and like something recurring is nice and efficient, but it actually makes very little sense if you kind of, mess up your first or next There is my son who just went, ich habe jetzt einen Termin. Kannst du bitte? Vielen Dank. Sorry about that. Life as a parent is not always easy. All right. So I was saying, why do we care that much about the next replenishment? Actually, because if we really do mess up the next replenishment, like the long term makes little sense, right? Like kind of, it becomes very difficult to catch up or to even make any meaningful decision. So what do we do is that, okay, so let's give a bit more freedom to the next decision, right? The next time of the replenishment, the next quantity. And then let's let the algorithm to plan, let's say, further like replenishment with some degree of freedom. So if we have a look at this policy, how it looks like this. So we want to basically define the T0, basically when you should next like 0 in terms of Python. So when should your first or next replenishment be? At which quantity? Given that we also give you freedom for afterwards to replenish if you need, right? Several times following this very easy policy. But we also give you a T-limit, which means that you will basically have to tell us when you think, given a certain, demand forecast pattern, when you think it makes no more sense to do replenishment or do any other operation. So from RSQ, we ended up to basically like a more realistic problem where we give a lot of freedom for the first one, and we say define your next, define some future replenishment, but also tell us when we think, or when the algorithm thinks we should stop even planning any like replenishment. So this basically, hopefully if you have like, let's say a seasonal pattern, right, where you have a start of the season, high season, and then end of the season, you basically want this to end up something like this, where at the end of the season, right, you have no more stock and you tell, okay, let's stop replenishing. We're out of the season. We're not, need to have anything. So you basically block it. And if you're basically running this every day, this is dynamic, right? So the decision changes, and basically every time your situation changes, like might be that your forecast changes, something happened in the price, something happened in the stock, some exceptional returns came back. Basically, this decision is adapted to being modified over time, and you have to run it on a regular basis. Yeah, so this is what we need to find. This is the decision space to optimize, right? So think about it for those who do like machine learning or deep learning, these are literally like your weights, basically. These are the weights that we need to find, but these weights have, a business meaning, basically. They're not the weights of a model, but they're the weights of your business, your supply chain, basically, space. So, yeah. How does the cost equation look like? So Andreas mentioned actually profit optimization. So basically more like profit contribution optimization, where we're trying to maximize it. And if we were like to remind that in terms of terms, that would be you basically sum up your revenue that you're expecting from your policy, minus the cost of shipping to the customer, the holding cost, minus the replenishment shipment cost, the return processing cost, purchase cost, and your alternative cost of overstock, right? Let's say at the end of the 6 months, you way too much overstock, you have to basically discount them or do something with it. And basically, take that cost. But to basically simplify the operation, we can also like express this not anymore as a profit contribution maximization, but as a cost minimization exercise, which is simpler to represent as long as we have the cost of lost sales, right? So like the cost of lost sales would be in your simulations or in your basically policy when you should have had stock to fulfill some demand, but you didn't end up having stock. So you weren't able to fulfill the demand of the customer. So you ended up basically losing money. And once you put that equation, then your reality becomes, okay, then actually we need to minimize this. Both of them are equivalent as long as like you respect this constraint, right? But often the cost minimization exercise is much simpler, right? And if you think about it, we're in a time where, like economically like difficult situations, and we're basically the concept of being cost efficient important. This is, like a pure example, right? Like we don't have to make any more decisions that are, random or they're not efficient. There is always a way to basically anchor your decision space and, to some economical value, like to some cost value. And if you want to be, efficient, then you can actually go and model that and then try to optimize that. So that's the main purpose of this exercise, right? Okay. This is how it looks like then. And if we were to visually like represent that, and then let's say on the x-axis we have our parameter set theta, and then on the y-set we have the function of theta, so basically like the cost that we're trying to minimize. Then we would ideally land, in this global minimum area, right? It's not fully convex, but we will also show you by plotting some cost space later on that actually like this type of linear equation, especially in inventory, they tend to be rather convex. So they're not, like the spikiest, or like you don't end up having tens of different, like local minimas, but you do end up having maybe a couple of local minimas, but still like you do have this like very nice semi-convex, or actually fully convex pattern. So it does become a rather, let's say, a nice exercise to solve. Yeah. And the policy inputs, right? So now we talked about the problem, the policy, so the decision space. We're like, okay, so Hagop, how do you make your decision space? So we're gonna talk about the inputs, right? So what do we feed in, basically like your features in this problem to end up having like your decision. So like a reminder, right? What do we even need to optimize policy? We have to distinguish basically between two categories, like I think Andreas already mentioned. What we know, right? Because we observe or we took a decision on already. This can be the current stock level, the price of the item, the processing cost, if there is a stock in transit that we started that is like on the way. What we do not know and we have to estimate, so basically this is pure, forecast, right? And this can be machine learning forecasting, it can be statistical forecasting, any type of forecasting, but you have to estimate them. For example, alternative cost of overstock, upcoming demand, expected returns, your lead times, many parameters that you already mentioned that basically, you have to forecast. So that's difficult because they are basically completely sometimes independent, upstream products, right? Demand forecast is one product, return forecast can be like another product. You basically have to take this already stochastic or probabilistic uncertain inputs, and you have to make a decision that accounts for the variance that you have in your inputs. So think about it, right? The problem is already pretty difficult.
So here I'll also make a kind of pragmatic comment, right? So I think many of you can probably relate to it being kind of sexy to do estimation. And it's easy for a business to get stuck focusing a lot on the estimation. But if you look at the overall problem, the estimation is a very clear means to an end. And an estimate can be as simple as taking the mean, right? If you imagine the policy we've been describing, you could take estimate a normal distribution for the demand and call it a day, right? That's still an estimate. And only when you need that estimate to get better, like a sharper probability distribution or less bias, that's when you start looking into more complex techniques. But of course, it's very easy to get stuck in investing considerably in your estimations when actually the policy might be where the shoe doesn't fit.
That's true, Andreas. I like the fact, and I think it's important to remind that basically any forecast, right, isn't like in this business environment is just a mean to reach a goal, right? So like the forecast will be a hammer, right? But if you basically have to take your nail, you have to take your painting, you have to basically put like the nail, put the painting. That's the end goal, right? Like having something beautiful on the wall, and that something beautiful then is like is your actually health of your business, right? Like how do you run healthy logistics operations? That's your end goal. And a forecast, as beautiful as it is, it's just only useful if you use it in the right way afterwards, so in the downstream application. And I think if I remember, like Andreas, like you actually realized that many people on online chats, and I think even we presented, or at least I did present demand forecasting a series couple of months or years ago, and you were basically wondering, or you noticed that people were wondering or saying, "Hey, now I have forecast, great. Now what do I do with it?" Right? So I think that's the type of conversation, and it's true that
I did with that title once.
That's true. So I have forecast now. What do I do with it? I think it's a good question. So let's see what and how do we do with it. All right. But before we go into like the actual mathematical solutions that we found and how do we solve this, so it's good that we even spend time on the concept of deterministic versus stochastic, right? And why actually there has to be a distinction and what passing from deterministic to stochastic actually even brings to your use case. And to do that, I would like to basically remind, right, that deterministic forecast as inputs, right? What do they mean? Is basically when you have 1 point per time of forecast, right? Let's say you're trying to forecast demand for next week, and then you end up saying next week I forecast I will have 500 units. The week after 550, whatever, right? So, but you always only give one value per forecast, and you do this for all of your inputs, right? Like you say that my lead time is 8 days. Right? My shipment lead time is 8 days. My return rate is 50% or 30% or 20% or whatever. But you basically always end up having one value, and you're very, very confident about that value, right? And that's deterministic. And I think that Alexei, we played this game together, but I still would like that we play it again. So I'm gonna ask you questions, and we then try to resonate if indeed it does make any difference. So Alexei, I first tell you, right, that we have a model that is forecasting that the demand for next week is gonna be 5,000 units. Okay, that's the information. And now I tell you, oh, actually, Alexei, I forgot we have another model that is saying that it's highly possible that one of these three distributions can occur around the same value, right? And the question is then, how would you reach this? Like, how would you take this input, right? Would you react in the same way?
Okay, so the question is, there is an estimate on the number of items for a certain product, right? And we know that this estimation is, so this was a point estimation, but there is some distribution around that estimation, right? And your question is, would I behave differently knowing that it's distribution 1, distribution 2, or distribution 3, right? Would I consider different things?
Exactly.
Well, I guess.
So let's say, like in this case, right, where you have this type of like Poisson process, right, where you
Yeah.
basically say, oh wow, I can actually have an explosion of demand, and that thing is rather sudden. What would
So,
you do in this case? Would you order more like in this case?
yeah, because like in first distribution, the uncertainty is like the variance is smaller, right?
Yeah.
So I'm more certain in my decision.
Yeah.
In the second case, like I'm less certain in my decision. And third is like there could be a spike, right?
Exactly. So basically, like what you said ends up being most of the time reflected in a very concrete, decision inventory, which is your safety stock. Basically, how much stock you want to have that you don't want to really touch or not
Right.
as much as possible. That basically is trying to account for that variance, like in the future. That decision is somehow implicitly done in the decision space that we think. You can specify it and like find a way in your simulation to isolate it and have a specific value for that. But when you do optimize in a nice way and you're having like this distribution forecasted, right, you actually have an impact on the safety stock. If you're like, the more uncertain you are, the more safety stock you will have. So as you said, right, you would basically have more risk pattern there. So Alexei, now I give you like the thing of the demand. Now I tell you another thing. Actually, your lead time can be 8 days. So if you make a decision to order, you can only have it in 8 days, not before. Someone has to pack it, has to make it like in a beautiful box, has to put in a beautiful, car, and that car has to route your like to your destination. And now I tell you,
Okay.
so even that has, sorry, so even that has, completely different patterns. So is it always possible that it's going to be 8 days, or sometimes it's 8, sometimes it's 6, sometimes it's 12? Your average is 8, but it's never the case that it will always be there. So that even there, you're not really sure. So add more basically uncertainty there. Okay. And now I tell you, Alexei, you're not lucky. All of your inputs have the same pattern. So realistically, there is no way you have confidence in any of your inputs, neither your lead time, neither like your demand forecast, neither your return.
And I also don't know the distribution, right? Or I have some ideas.
It's up to you to make that decision. So there's a choice where you basically are a bit more adventurous and you make a decision on the ship. So like, like a prior. And
Because you have some prior data, right?
Sometimes you can. But for example, like for the demand, you can't. For the lead time, you do observe some patterns, so you can basically make some priors. But for the demand, you can't, or you basically have to make really, strong assumptions on that. Huh?
Why?
On the demand? Well, let's say you have millions of SKUs, right? One SKU can have, a Poisson distribution. The other can have Gaussian. The other might can have gamma. Basically, are you ready to make the assumption that all of your SKUs have a demand pattern that on any given time t will have the same distribution for all, right? Is that really?
I can give you one example that is really tough if you try to do this, right? So the distributional assumption you would make for an article that sells maybe one item a week. You don't know exactly which day, but usually in a week you sell one item, or an article where you sell 1,000 items per week. So for the article where you sell 1,000 items per week, you could do something like a Poisson distribution, right? But for the article that sells maybe one every week, it's super zero inflated. And actually, the way it turns out, with millions of articles in your assortment, you can say that most articles never sell on average. And anyway, you end up selling hundreds of millions of items. So already kind of transitioning between your top sellers and the vast amount of still selling slow sellers you already find that you need to use two distributions.
Yeah. So that happens. And again, Alexei, right? You don't have to have the same way of solving it for all. It is possible that you like your lead times, you do have a bit more observability, right? So you can go with one technique and make an assumption. For the forecast, you don't want to take that risk, right? So it really is possible that, which we did actually. And for every input, we approach it like in a different way. But we try to have still that, variance estimation exercise accomplished, more or
But
less.
Hagop, you're bold to say you can't. That has a tendency to make academically minded people want to find find wrong.
That's true. No, so we try, right? So I mean, you can never guarantee, but basically, that's the exercise, right? And sorry for the academics if you offend them. I hope not. We love you very much. All right. So the main conclusion is that if you take deterministic, right, and it's often a good baseline, you do find out that you actually end up in not making yourself safe against basically, the unexpected of life. All the uncertainties that Andreas mentioned at the beginning, right, like the strikes, the pandemics, the demand, all type of noise and any of your inputs, if you don't take them into account, well, guess what? You actually do see a very massive difference in the final decision space, right? So you can play a game. You basically, sample, or you don't sample, or basically you take the mean forecast or you take the distributional forecast and you try to do like the same operation. You do end up in very different decisions, right? And that decision has a final, very different final outcome on your economics. So the main point is that if you go deterministic, that thing actually tells you nothing about noise, right? Like how much noise is there? Is it high? Is it low noise? How much confidence you are in your decision when you say, okay, I should replenish that amount, right? Should I have more safety stock, less safety stock on this one? How does this confidence evolve over time, right? Like the further I forecast, how is it the forecast? Am I, certain about it? What should I do for that? And yeah, it's not easy, right? Like modeling this is not easy. Modeling variance is not fun, right? Already modeling mean, like if you want to model mean is not easy. And if on top of that you want to model mean and variance, well, good luck, right? That's the thing. But it's possible. And that's what we try to do. And we try to keep this basically concept of end-to-end stochastic, not only in the inputs and not only on the forecast, but also take that also concept of stochasticity in the optimization process itself. So end-to-end, capturing the variance. Otherwise, it makes very little sense to have, probabilistic forecast, but you do nothing with it. It's basically pointless. So that's what we're gonna try to speak about now and how we, actually ended up doing something with it. All right, and I think Andreas, this is up to you, right?
This is where I come in. Hit it.
Nice.
Cool. So with the risk of sounding a little bit like a broken record, it's a two-step flow, right? We want to optimize the decision. It's a policy. To make the policy, you got to put something in the policy. You might have to estimate some of that. All right, cool. So first, we build demand forecasts, return forecasts, a model of costs, a model of lead time. So now we have either known or estimated everything we need to stick into the policy. Then we implement a policy optimization engine. So now we're saying, okay, given all of these parameters that comes into the policy, I need to solve an optimization problem. I need to find the replenishment decision that, given the parameters, gives me the most profit contribution. This is all nice, but of course, how do you get uncertainty in there? Well, there are two kind of classic techniques. One of them, you make a convenient distributional assumption, by all means, works. And that way you could solve that analytically in some cases. And the other one, let's say the more pragmatic method, you bring out the good old Monte Carlo toolbox. And actually, I will say, as you will see in the later slides by Hagop, Monte Carlo is very attractive these days with easy access to compute. All right, so we made internally, of course, this consideration ourselves, and we kind of came up with this consultant level overview of the situation. And essentially we're saying, well, so you got reinforcement learning, you got Monte Carlo simulation, you can do a parametric stochastic modeling, and you can do deterministic modeling. And we kind of put these in two axes. So we could say, what's the complexity of your problem you're trying to solve? and what's the risk of the solution approach you're taking being not feasible. So deterministic modeling, it's if your problem is very simple, it's kind of very easy to see how the feasibility is high, right? It's not a big risk. If you're having a simple problem, you can do some back of the envelope calculations and you can come up with a replenishment decision. In fact, I would hazard for most of the replenishments that happen in the world, this is the way it works, right? You have someone with an Excel sheet, they put in the factors, they have some equation, and they come up with a decision, and then they adjust as the world evolves. So of course, very feasible. Then you can do parametric stochastic modeling. That gets you a little bit more into the complexity, right? So you might actually want to account for some uncertainty. The problem, as we discussed before with parametric, is that you end up finding that you need to use multiple different distributions, or distributions can start becoming a liability for you in this. And then you look over to Monte Carlo simulation, and you're like, well, actually, the assumptions I need to make for Monte Carlo simulations are pretty attractive. And these days, with the accessibility you have to high performance compute, the cost of Monte Carlo isn't really that high anymore. So I would say this is actually almost somewhat of a shift in the industry as of late, that which kind of came on the back of all of the compute we use for deep learning. All of a sudden, you can put your Monte Carlo simulations on the GPU easily, right? Which historically would have been pretty tricky. And then, of course, reinforcement learning is perhaps for this problem, it is attractive if you're curious. Let's say if you're academically minded, you're seeing this problem, you might say, yeah, reinforcement learning would be an excellent training ground for reinforcement learning, which is true. If your goal is to practice reinforcement learning, this is an excellent problem to practice it for. If your goal is to make great replenishments, reinforcement learning might be a little bit too data hungry and a little bit not feasible, especially once you're coming into modeling a complex domain. So with that, you'll see here, in our case, we're opting for Monte Carlo simulation, very attractive for us. So what's happening here, right? So we're estimating to the left, the demand forecast, the return lead times, the lead time of replenishment. We're looking at the economics of the decision that needs to be taken. You essentially take these parameters, put them into your Monte Carlo simulation, and then you essentially explore the decision space. And for each potential replenishment, you can estimate what roughly the profit contribution should look like, or even what the distribution of profit contribution will look like. And so then you might want to be a little bit robust. The absolute simplest technique for being robust here, this is really the absolute simplest way. Instead of optimizing the expected value, you can optimize a quantile. And then this you essentially have from a purely programming standpoint. You know a function, Monte Carlo simulation, parenthesis, my proposed replenishment. I get an objective value. Oh, the Apple sent balloons. I think I can do it again. Yeah. Oh, go back, Hagop. Go back. And then, of course, this is a perfect formulation for a optimization solver, right? So there are plenty of good, actually gradient-free black box optimizers. Usually, the limitation with those is that you need to have a somewhat well-behaved loss surface, and you need to have a low-dimensional decision space. Now, thanks to the inventory policies Hagop spoke about before, we do have a small decision space. So we can actually do this. So how does this look in reality? Now, Hagop alluded to this before. We end up with a fairly nice decision space. So if you look, and I think the best part here is the top left one, right? So here you see in color the objective. Purple is you make more money. Yellow is you make less money. And for the initial replenishment quantity, Q0 on the y-axis, and then T0, the time of the initial replenishment on the x-axis. And you can see that actually the objective surface is very well behaved. This is, if I think I can see somewhat of a non-convexity, but this is certainly monotonically increasing. So easy enough to optimize with a gradient-free optimizer. The rest of these, you can imagine I'm just scanning over the decision space, putting constraints on the remaining parameters and seeing what the remaining parameters come. It's an interesting exercise to look into this. I'm mindful of time right now.
Yes,
so,
so for them, Andreas, yes.
do you want to do these, Hagop, or?
Yes, I can do. So basically, the question is, okay, so Hagop, like you or Andreas, so you mentioned that you're sampling, right? Like you're sampling and this and distributions. How do you even actually get your initial input to sample from, right? So this is then the question of how you forecast your probabilistic, inputs. So there are many ways, right? Like you have basically Bayesian methods or frequentist methods, but we want to focus on the frequentist methods because they are the most common ones, specifically about how you basically learn your distribution parameters or how you learn directly quantiles to sample from. The first thing is basically this is what you mentioned, Alexei, right? So you basically have to make assumptions on your distribution around the forecast. Let's say you say I want my demand to be following a Gaussian distribution around the value or a Poisson, then you actually end up learning the parameters of that distribution, right? Either mu and sigma or lambda for the Poisson. And you say I want to basically learn this with my demand forecast or my return forecast on historical data, doing basically log-likelihood maximization. And then once you have your distribution parameters, then you have your parameters, right? You basically just take your distribution, you put in the parameters, and then you sample from that value in a random way. That's the first way of doing it. The big disadvantage is that you have to make assumptions about distribution, and that's never guaranteed that it is gonna work. The second way of doing it is you're like, okay, I don't want to make any assumptions. I want to learn directly the quantiles of the distribution, right? So you then actually end up learning the quantiles. And this is like many methods. And one of the best way to doing it is using the quantile loss, right? So I already mentioned about this in the demand forecast series, but basically it's the same content, right? So once you have your quantile matrix, so let's say you forecast every fifth quantile, 5th, 10, 15, 25 until 95. Then you have a matrix of 20 or 50 quantiles or whatever quantiles. And then you can just sample the quantile index following uniform distribution, and then just take that value in the simulation. So instead of sampling from a distribution with parameters, you basically sample directly from the quantiles following uniform distribution. Both of them work. It really depends on if you really want to be adventurous on making an assumption about the distribution or not. But both of them are valid. Definitely. And the question is, okay, so you told us the problem, the solution that you found, the sampling and the Monte Carlo experimentation, and basically how do you, scale this up? Because
Hagop, I was just thinking, we don't have a lot of time and we have quite a few questions.
okay.
So what do you think? Do you think you'll?
I will make it on time. I will make it on time. 2 minutes.
Questions. 2 minutes, okay.
Maximum. Basically, like the slides, and it took much longer than thought. But I think this is basically the good thing, right? Like the good news is that, and the conclusion of this is that basically Monte Carlo simulation has been seen really like a blocker, right, for many, where they try to go up and do crazy mathematical modeling, and then they validate the modeling with simulations, but they don't take the simulation as a first solution because it's expensive to compute, right? Let's say you're doing a grid search with NumPy for one article that took for us 45 seconds with 2,000 or 3,000 demand trajectories. From basically 45 seconds, we managed using accelerated simulations with NumPy and IntelliSVML, and using SciPy and Shigo as optimizer, we ended up actually bringing that value to 200 milliseconds. So basically, the entire engineering work was, okay, how can we make the simulation possible so that we don't even have to make any assumption about the mathematical, but let's just take the most realistic model, which is the simulation, where really we allow the complexity of our work in it. And there you can put anything in your simulation. And that was basically possible thanks to NumPy. You can use JAX, you can use any compiler, but you basically have to get out of pure Python. You have to find a way to compile your code, and you have solutions. And this is what we found. Now the questions. Yes.
So you finished.
Yes, I'm done.
So number for the win, right? Or
number for the win.
Yeah, really awesome tool. So you showed that you optimize for quantiles, and in particular, I think in one of the slides, I think Andreas was showing that it was Q75, right? So you try to optimize for this cost quantile, right?
Yep.
Does it mean that you're a little bit more, let's say, pessimistic and you replenish sooner rather than later to minimize costs?
Yes, we want to be like risk averse.
Yeah, so we're a little bit pessimistic, I'll say, but it's not always working out to sooner. So that depends on the order economics. So if you stand to lose more from overstock, then being pessimistic means that you replenish less. Whereas if you stand to lose more from lost sale,
Yeah.
being pessimistic means more. So it's
Mhm.
a little bit more complex, but roughly that's the way to think about it. 75 here is just a number we pulled out of thin air.
Mhm.
It's not actually what we're using.
And don't forget that we have an actual human using this tool, right? Like the human puts some of the parameters, and the human, there's always a chance that the human makes a mistake. So we also want
Yeah.
to count some input mistakes.
Mhm. And so when it comes to humans, operators, like how important SLAs are, like you mentioned that you can do it pretty fast.
Yeah.
And being fast, like how does it impact your models?
So if you do, I mean, basically you have to, so the problem isn't the optimizer, right? So because when you have like an optimizer here, for example, you have to make a choice, right? Like the best solution is obviously like if you do like a grid search or you do like brute force, you go to the entire space, that's the safest. But is that really like realistic, right? So you just have to make a choice, either like Bayesian optimizer, either some hyperparameter optimizer that we use from even machine learning, or like a global, black box optimizer. So this is where you basically lose something because they have to sample. And the question is, how well can you sample and compute or not derivatives? So in this case, it's derivative free. How can you basically represent with as minimal point as possible your entire space and then find that, minimal point? So that's where you have to lose some basic risk. Sometimes it might not always converge, but that's the risk you have to take that, if I want it to work for like an average and which you check, I have to make it, fast.
You run it
That's
for
about
all
the
the articles, right? For all the SKUs.
Yeah. So when, for example, the user like in real time puts a parameter, let's say they update the price of like the average production rate, right? They say I sell a product and average I pay 35% to buy or build that product. Then basically we have to update the entire recommendations for all of their catalog. And this happens in an async way, and every second matters.
And there are quite a few questions from Adrian, and there is one question from Rosona, but we unfortunately cannot cover them because we need to wrap up soon. So, Hagop, Andreas, is it okay if people can contact you directly through LinkedIn or some other means of communication?
Absolutely. Hagop, go to the last slide.
Yes, the last slide is this one.
Okay. Okay, so take a picture, everyone. I mean, not with your phone, but a screenshot. And this is how you can contact Hagop, Andreas, and check the first link, also important. And I want to thank you, Andreas, Hagop, for being here, for presenting. That was very interesting talk, and I expected nothing else from your previous talks. So I knew that this one would be really great. It's packed with a lot of stuff. I learned quite a few new things. I had no idea like how actually these things work in practice. So thanks a lot. And thanks everyone for attending the talk too. So I hope everyone learned something new today.
Yeah, everyone. Thanks, Alexei.
Yeah, have a great evening, and yeah, tell hi to your son and wife. You spoke in both French and German, right? I think that was like, I was thinking like, which language did he speak? Like,
My
I think
life is complicated. Alexei, sometimes like we speak 5 languages at the same time. I'm like, Jesus, I have to do something about it.
I can
okay,
imagine
now
Hagop
go
loses
speak
count
your
of the
languages.
languages he speaks.
Yeah, okay. And I'll go speak mine. Okay.